Cool. Okay, so Stan, before we get to the case study, which is very exciting, applying all these ideas to a single project and making discoveries, which is next week, we're talking mud volcanism. We're talking the top of this system, Stan. We're talking what's happening basically today from the subcritical, supercritical boundary, where water changes from non-ionic to ionic, and things really start happening in the upper crust. And then it really, for me, it was the idea, all right, if you look at the Permian Basin, for example, and they started drilling it 100 years ago, and they started driving out this shape, and it was very obvious with not too many wells that it was a big bowl. There's a big bowl here. What's going on? So the idea of mud volcanism that's making a bowl shape and filling itself up majority from the bottom, you would say maybe 80% of the sediment in that bowl is from the bottom, and maybe 20% is shedding off the shelves, correct?
If even that.
If even that. So for me, I'm going, the mechanism to create a bowl as the mud volcanism's coming up, it's creating this positive feature, but we're talking 200 million years ago. So this is an old system that now looks like this big bowl, but our mechanism, our model is saying that it's coming from the bottom up. How is this basin filling from the bottom up? That's the end of the program. That's the end.
Well, and you're looking at a model for that right here.
Yeah. We're going to talk about that, and you got wait until you see these videos. Oh my gosh, these mud volcanoes that are coming out of the ocean's bottoms. I mean, incredible, incredible, incredible. And I think make an impact on what we do and how we understand these reservoirs without question. The models are there, but the upper crust geology, Stan, is huge. It's a big subject. So with that being said, let's kind of attack this outline. There's a lot here, folks. We did a lot of work, and it's going to take time. At the end, we'll talk about specifically mud volcanism and the upper crust geology, but we got to talk about and give our credit where credit is due in the overall scheme of the upper part of the UDH model, which is what we're going to do first. That's the first half of the presentation.
Right. So a couple of key concepts here that you people are familiar with the terminology, but from a UDH perspective, they have a completely different application. One thing to get your head around is that these hydrothermal plumes, going deep to seep, are crustal scale. We saw some of that last week up in the oil sands where there was a seismic section. We should have put that one in. Where you can see evidence that the entire crust has been affected by some kind of fluidization event. Mm-hmm. But you can open up your last week's presentation to look at that.
Crustal scale, you're talking the lateral and vertical scale of the
That's
the
right.
crust.
These occupy huge rock volumes. And then there's basically a fairly consistent recurring mineralogy that in it, that it has sort of a sequence to it, that it's characterized, and all of these are result in huge mineral deposits. For example, these hydrothermal dolomites, but they're not all of this, and all of these ultimately they're interesting because they have oil in them, which occurs typically at a certain point in the sequence. But the key is that they're not a conventional rock type. They don't conveniently fit into the threefold sedimentary igneous metamorphic story. And so as we pushed along on that, at the end of the Gouda thing, we realized maybe we're dealing with another rock type entirely, a fourth rock type, which for now, we're still test driving this, traveling it under the term hydrothermalite.
Right.
And comments from the peanut gallery are welcome.
Of course.
Anybody comes up with a better one, we're going to steal it.
So real quick in the outline, give us your cleanest, your most accurate definition of authogenic or authogenosis, diagenesis, paragenesis.
Well, and that fourth rock type idea feeds back into this. So the hydrothermal, basically you've got to understand your diagenic process is, from our point of view, dealing with these crustal scale plumes is a hydrothermal diagenetic process. So we're not dealing with burial diagenesis. We're taking an existing rock and we are adding an outside exotic hydrothermal component to it that has to do with that mineral list that you see below the title. That you can refer to as authogenic. So authogenic means minerals that have come into a rock after it was forming or formed.
Okay.
They weren't native to in the conventional sense, the local sedimentational environment. And then they typically drop out in a sequence, which starts out with early dolomite, then you have anhydrite, quartz sulfides, oil, calcite, clays. And we'll go through each one of those in a bit more detail. But that's called paragenesis, or the mineral sequence that's associated with the orthogenesis.
Okay. I'm following a little bit more on that one. Now, diagenesis is simply a change in the rock, like metasomatism. It's just a change later in the rock. It's really vague.
Yeah, it's anything that happens to a rock after it initially forms.
Orthogenesis is anything that happens to the rock, but specifically getting to add new things into the environment.
Usually involves a chemical component that's been added, yeah.
And paragenesis
is the sequence of the addition.
Is like forming oil in a clay. That's a paragenesis event.
Well, yeah, but it occurs at a certain point in the sequence. You can think of this as a high magnesium fluid, but it has lots of other things in it like sulfur, kerogen. So all of those things participate in what you could review as a reaction sequence, which starts out with some early stuff coming out, then later, then quartz, etc. Basically in the way you're seeing it on that list.
Okay.
So it's kind of a reaction sequence.
Okay, paragenesis.
Yeah.
Reaction
and another
sequence.
way to view that is it's a fractionation sequence. So the first thing that these things are coming in very magnesium rich.
Right.
So the first thing that tends to supersaturate and drop and find something, i.e. dolomite, is one of the first things to come out. And as we'll see, it comes out in two ways: an early sucrosic thing under the hot, more supercritical conditions, and then a later, more what we call saddle dolomite. And boy, we got a great picture of one of those that we got out of Mindat. So then once you remove the magnesium from that, then you've changed the chemistry of the brine.
Mm-hmm.
And it's typically what's next. Well, the silica is usually what kind of supersaturate, plus or minus calcium sulfate. And then the sulfides supersaturate. So they basically are saturating in the order of their original concentration component in the brine. So you got to fractionate one, and then you'll get another one. And so for those that took a petrology course in hard rock, you're dealing with the Bowen's, sort of a fake Bowen's reaction sequence, because that's what the Bowen's reaction sequence is a fractionation event where you remove ironically, the magnesium-rich rocks like olivine first, and then you wind up with quartz and feldspar down the line.
Wow.
So not totally dissimilar to this.
No. Wow. Okay. That's a big subject. We're going to talk about that. Importantly, and what needs to be said in this, and for us as applying this to oil and gas industry, for example, orthogenesis or orthogenic mineralogy is stripping out oxygen and allowing hydrogenation of kerogen. So you want to find yourself in these rocks especially the ones that are really stripping out the oxygen. You want your wellbore in that environment to have the biggest bang for your buck. That's where oil was being made the best.
Well, yeah. So again, we talked about removing magnesium from the brine, but the other thing is that all of these minerals remove oxygen from the brine, except for the sulfides, obviously, but they remove sulfur from H2S gas components, so that frees up hydrogen. So the bottom line is that all of these mineral depositions consume sulfur and oxygen and release hydrogen from the brine component. Now, you've got kerogen floating along for the ride here.
That's right.
And the first thing that hydrogen wants to find is that kerogen, and it hydrogenates it. And one of the things it does is that it makes diamonoids.
Yep.
By rearranging the polyaromatic component of the kerogen into things like hydrophenanthrines. And then those rearrange as the more hydrogen is added into actual diamonoids, which then, as we were talking about in the last webinar, the diamonoids then provide molecular platforms on which you can, and bridge points on which you can then start polymerizing alkane hydrocarbon chains. So and that's why diamonoids are on in every oil, because they're, to summarize what we said last time, they're typically bound to the kerogen by weak van der Waals bonds, and so when the alkane chains gets too long, and they're represented in Iraq-Yaval analysis as S1, then that breaks loose as a fluid, i.e. oil.
It could be obviously a structural event too. It could be a depression.
Oh yeah, there's a lot of mechanics that can
Okay.
aid and abet that process.
And out of all those things that we could talk about, we're going to pull out mud volcanism, Stan. We got to do this.
Yeah, he's really hot on mud volcanism right now.
What's
All
cool is, the Mars analogs, the modern analogs that are happening out on these ocean floors and at the surface, like Lucy, the mud volcano, the Caspian Sea. I mean, we went out there and we really
we should have put Lucy in there, but we'll do that next. We'll do that in the expanded one.
So let's get started. What do you think?
Let's do it.